Hello, my name is Luigi Vanfretti. I'm an associate professor at Rensselaer Polytechnic Institute, and I would like to present to you the work that we have done with Narasimham Arava of GE Digital on decision trees for voltage stability assessment. Here's a brief outline of the presentation. I will briefly discuss in general terms voltage stability assessment, and why we're using decision trees. The second part of the presentation discusses the two methods that we use to train decision trees to perform voltage stability assessment. This is followed by some case studies and results obtained, and finally I wrap up our major findings. Voltage stability is the ability for the power system to sustain a fixed tolerable voltages at every bus under normal operating conditions, as well as being subjected to a disruption. So this leads to two mechanisms that result in voltage instabilities. One is where the demand cannot be met by the available generation system due to transmission or reactive power limitations. This typically happens due to small load increases and limitations in transmission capability, whereas the second major event will affect a portion of the generation, like loss of a plant, or transmission system, like loss of important lines, in such way that you cannot meet the pre-fault demand, the load, with the available remaining generation transmission capacity. Now, voltage stability indices were developed to really deal with the first type of situation, and these indices help to foresee unacceptable effects on load increments. Now, voltage stability assessment is a systematic methodology in order to assess or to determine if the system will be stable under different type of contingencies and conditions. Usually we consider the power flow feasibility conditions and the voltage stability boundary associated with singularity conditions of the power flow Jacobi matrix and the Saddle-Node Bifurcation. The conventional methods used is the continuation power flow and direct methods. The continuation power flow has reliable conversion due to predictor step, corrector step approach, but is very computational intensive, whereas direct methods are very sensitive to initial guess. To obtain a full voltage stability boundary, the computational effort is very significant for large-scale power systems. So due to these different challenges and limitations, we combine these different approaches, and we attempt to use decision trees to perform voltage stability assessment in a fast fashion.
So why did we choose to use the decision trees, even though it's like a very old technique? Well, decision trees and any other sort of database or machine learning technique can create a model that is based on historical data, okay? It's not a physics model. Well, decision trees are attractive because they are kind of a white box, so you can know and understand how they are working in a very easy way. Now, as with many other data-based models, these ones do not explicitly represent the physical system, but you basically have a mathematical relationship between input and output measured from the system. In this case, we're going to use models, physics-based models. So the accuracy of this machine learning-based model, or the decision trees, is really dependent on the accuracy of the simulation outputs that replicate the original system. So we inherit those basic limitations also. However, there is this PMUs going around since I was a grad student. So real-time security assessment is becoming attractive. And basically, if you have a decent enough model and you have trained decision trees, you can actually use this for improving these real-time security assessment systems. So that's the basic idea of what we're aiming to do. We're trying to provide some look-ahead capabilities through decision trees.
So in this work, we have applied two different methods in order to train decision trees to perform voltage stability assessment. The first method is the voltage stability indices method. And the idea here is that we use the indices to classify different types of contingencies, and then this will be used to generate security rules using the decision trees. And this can be used as a recommendation, these rules provided. The other approach is a region classification method. And here what we do is that we propose a new classification criterion that enlarges and generalizes the existing security boundary that is used, where we simply separate the conditions between stable and unstable. So we want to expand that to have more granularity and to be able, therefore, to provide better basis on taking corrective actions. So this is going to be based on the distance to the nearest Saddle-Node Bifurcation. And yeah, these two methods are aiming to be used to derive both preventive and corrective actions, and those actions could be later provided in a recommender system for the operators or in automatic schemes such as load shedding. So the first method is the so-called voltage stability indices method, and here we use a 3-layer severity index that allows us to classify the output from dynamic simulations of different contingencies. So the index actually will provide us a measure of the system of how far it is from the maximum loadability limit. The workflow used to compute the security rules follows the triptych anticipate, analyze, and classify, which is depicted in the figure below. We have a dynamic model and a specification of the simulation scenarios for each contingency. In the anticipation phase, we have to extract the potential starting point so that we can initialize the model and simulate. So that's done by sampling the operating space. Then we perform dynamic simulations and we basically analyze the results of the dynamic simulation through the index. So the index provides a mean to basically extract information from those waveforms. And finally, in the classification stage, we're going to synthesize some security rules. The security rules are basically thresholds on specific variables that discriminate between secure and insecure states. Finally, this approach actually is what is adopted in this iTesla platform that was implemented and tested some years ago by w.r.t. So the output of the simulations are going to be classified by the voltage stability index as safe or unsafe. These safe or unsafe cases are going to be used to train the decision trees and then generate security rules. The security rules, the boundary, they are mapped against physical variables such as active power, reactive power, voltage, and they're influenced by the set of contingencies and security index pairs considered. Pictorially, this will look like in this case that we over here that we have all the cases that were sampled, and here is the boundary, which will be our security rule. So these security rules are expressed as decision trees, and they're very easy to interpret, and they can also be used as linear constraints in optimization problems or tools if you wanted to derive corrective actions. So the decision trees help to characterize this power system security for these predefined contingencies, and also minimize the amount of simulations that you have to do. We will use two approaches to generate the decision trees in this workflow for each contingency and security index pair. There is the worst case approach. Here there is a set of candidate attributes of the decision tree. They can only be related with power variables. While the Monte Carlo-like approach, here we'll have the attributes of the decision tree, can also consider other type of network variables such as voltage. Now in the region classification method, the decision trees are going to be trained on data from obtained from the power system network models. In each topology, there is going to be a base case for each topology, and for different cases of the contingencies, a database is created with all of the power flow results for different low power consumptions. So in this approach, we're not going to do dynamic simulation, but we're going to do something very similar to continuation power flow. This database of results are going to be used to predict voltage stability, considering the measured load, well, not measured, but synthesized load powers and voltages. So this is sketched here. We select the network configuration. We select a specific load bus. We simulate all of the load changes for each load bus. We segregate the database into training and testing data sets, and then we will train and test the decision trees. So in this method, we will train all the decision trees with respect to every load bus for each network configuration. So the number of decision trees obtained is going to be proportional to the number of load buses and topologies considered. The number of branches of the tree thus is going to increase with the number of cases. This is going to increase the size of the tree, which makes it a little bit hard to understand, and it will increase the computational burden and lookup time. So what we do is that we carry out continuation power flow for different network configurations with different load variations, and those are used to train and test the decision trees under those conditions. So the CPF, or the continuation power flow, allows us to find these solutions for each scenario, and it has a good convergence due to the predictor corrector approach, but it's also computationally intensive. So what we had to do is that we combine both the CPF with a direct method that just the SMB. So then we can do it, basically, we decrease the computational requirement. So instead of running the continuation power flow at all operating points to trace the unstable boundary, the CPF is executed just to obtain a good initial guess. So we start, the CPF method goes in this direction in the load increase, and once we find the boundary, we basically solve for the next point with a direct method. Then we use the CPF again, then we use the direct method again, and so on. And that allows us to trace the boundary quite easy. Now, we need to somehow measure with respect to the current operating point how unstable you are from that boundary. So what we do is that we take the Euclidean distance for every operating point with respect to the bus that you're considering. And we calculate this with respect to the boundary that we found. So this gives us the distance to the boundary, and the margin is calculated by dividing the distance by the nearest unstable point, which is selected based on the distance calculated to all the unstable operating point on the boundary. So in this method, the new approach that we have is that we're going to give you a more granular classification of all the operating conditions depending on the margin calculator and the minimum voltage. The decision trees are then trained on these classified operating points. The case studies that we carry out are the following. We perform 10 different contingencies for different operating conditions on this Nordic 32 system that was built into the iTesla platform. Within the iTesla platform, decision trees are generated by the Data Maestro software from Pepit, which was integrated there. These decision trees help to characterize the power system security for predefined contingencies and to minimize the amount of network simulations. So what we did is that we have 10,000 snapshots. Each of these snapshots represents one power flow condition. And then we have for all of those 10,000 snapshots, we have 10 different contingencies. The outputs of the contingencies were computed from a simulation program available in the platform. In those days, it was Eurostag. I don't know what they're using now. And the selected contingencies contain transmission lines whose average load is more than 65% of the nominal range. So this is the way that we're evaluating the voltage stability index approach. So to illustrate one of the scenarios here, we're going to consider the contingency where we remove this transmission line. And when removing that transmission line, we'll obtain a voltage instability in 11 out of the 1,000 snapshots that we have available. When we do the training and the testing, it looks like this. So we have the Monte Carlo-like approach, and we have the worst case approach, decision trees. The Monte Carlo-like approach actually classifies the safe and unsafe operating points correctly, whereas the worst case approach fails to classify the unsafe operating points correctly. So only the Monte Carlo-like approach is going to be considered in the sequel. So the decision tree that we generated is very much in line with an operational rule that defines a limit on the power flow in the region. So here you have the limit defined by the rule, and here we have the flow that needs to be limited. So this input flow is heavily correlated with variable with the underlying 400 kV topology and doesn't really change that much. The performance of the rule is quite satisfactory with applied to this data set. You will see here the predicted class and the true class. And you see that we have a pretty good performance. It's only 3 and 2 misclassified cases. Now, in contrast, we have the region classification method. This was a little bit newer approach, so it wasn't implemented in iTesla platform. So all of the calculations were done under MATLAB using the PSAT tool. Another issue is the iTesla tool didn't have continuation power flow, so we had to do it in a separate environment with the same model. Here, the classification rules are used to classify the operating points, and the decision trees are trained on the classified operating points and validated using the holdout validation of 20% on the training set. The performance is tested with the test data set. So here is a result of the region classification method. The performance of the decision trees is shown on this plot over here. Misclassification occurs in the boundary region because of the decimal values of the load powers and voltages. So this can be reduced by increasing the sampling in the boundary region. And the plot that is showing you here is all the stable and correctly classified as stable cases. The blue one is outside grid limits and correctly classified outside grid limits. And cyan is the marginal stable case and correctly classified as that. Whereas you see we have some red points here that was unstable. And then you have here on the outside grid limits, which is incorrect. And you have marginally stable in the yellow squares. The misclassifications are not that bad if you take into account the number of cases that we're evaluating. So the accuracy is pretty good, but you can also see the number of samples that we're thinking are quite massive for the training with this region classification method. To conclude, we have given 2 different methods which can be used to train decision trees in order to perform voltage stability assessment. And this can, of course, help to derive preventive actions that can be given as recommendations to system operators or be used as part of automatic load sharing schemes. Now, the voltage stability index classification method is less intensive computationally. It only needs some few contingencies to train the model. It takes less time to train the model, but it's also the resulting trained model is less accurate than the one based on region classification. The prediction accuracy is lower for default on the scenarios of the network that were not considered in the training set. So if you didn't simulate it, you're going to have really low accuracy for that compared to the other cases. Now, the region classification method is very intensive. It trains potentially the entire set of network scenarios. It takes a lot of time to train, but the trained model therefore is more accurate. The prediction accuracy of the trained model is lower on the boundary of the classification region, but that can be further improved by adding more granularity in the way that is trained is done. Thank you very much for your attention.